To the second part of topic metabolism. So last time, we mapped out all the major highways our body uses for energy, right? Well, today, we're going to look at what happens when you get a massive pileup on one of those highways. We're diving into the high-yield inborn errors of metabolism that you absolutely positively have to know for your board exams.
Okay, just take a look at this graph. I mean, it's beautiful, right? It shows how seamlessly our body switches gears on fuel. A super fast sprint, boom, you're using ATP and creatine phosphate. Settling in for a long run, you're burning fat. It's a perfectly tuned engine. But for the USMLE, the money is in knowing what happens when a critical part of that engine just breaks. What happens when these pathways go wrong? That's what we're all about today.
So we're going to start with the building blocks of life themselves, amino acids. Now, normally they're great, but when the enzymes that break them down are defective, these essential molecules, or their byproducts, can actually become toxic, and that leads to some really devastating consequences.
So first, let's look at how things should work in a nice, healthy pathway. See here? Everything kicks off with phenylalanine. With a little help from its enzyme friend, phenylalanine hydroxylase, it turns into tyrosine. And from there, tyrosine is a superstar. It's the precursor to thyroxine for your thyroid, dopamine for your brain, melanin for your skin and hair. It's just a clean, efficient assembly line.
Okay, now for the high-yield stuff. What happens when we break that assembly line? If phenylalanine hydroxylase is deficient, you get phenylketonuria, or PKU. Phenylalanine just piles up, and its metabolites give off this classic, musty, or kind of mousy body odor. Super high-yield buzzword. And since you can't make tyrosine, you end up with fair skin and, critically, intellectual disability. So what's the big takeaway? In PKU, tyrosine becomes an essential amino acid. Now go a little further down the line, and a defect in homogentisate oxidase causes alkaptonuria. The buzzwords to tattoo on your brain, black urine after it sits out, and ochronosis, that weird bluish-black pigment you see in connective tissue.
Another huge one you've got to know is maple syrup urine disease. And honestly, the name tells you pretty much everything. It's a defect in breaking down those branch-chain amino acids, isoleucine, leucine, and valine. This leads to urine that literally smells sweet, like maple syrup or burnt sugar. And this isn't just some quirky symptom, it causes severe neurological damage if it isn't treated. So for your boards, if you see sweet-smelling urine, your brain should immediately scream MSUD.
Okay, so we've covered our building blocks. Let's shift gears and talk about our short-term energy reserves. What happens when the body's sugar cabinet, our glycogen stores, can't be opened or even restocked the right way?
So this diagram really shows you how central glycogen is to everything we do. The liver, it stores glycogen to maintain blood glucose for the entire body, especially the brain. The muscle, on the other hand, is a little more selfish. It stores glycogen just for its own use during exercise. So when we're fasting or working out, we've got to break this stuff down to get that glucose. After a big meal, we need to store it. Any broken enzyme here is going to cause massive problems.
And here they are, the highest yield glycogen storage diseases. First up, von Gierke's disease. The defect is in glucose 6-phosphatase, which means the liver can't release its stored glucose. What does that cause? Severe fasting hypoglycemia and a massively enlarged liver. Classic. Then there's Pompe disease. The mnemonic is perfect. Pompe trashes the pump, meaning the heart. It's a lysosomal enzyme defect that leads to cardiomegaly. And for McArdle disease, another fantastic mnemonic, McArdle starts with M for muscle. These patients get these awful, painful muscle cramps with exercise because they just can't tap into their muscle glycogen.
Now let's put the two that students always mix up head-to-head. Von Gierke is a liver problem. The patient can't keep their blood sugar up when they're fasting. McArdle is a muscle problem. Their blood sugar is fine, but they absolutely cannot tolerate exercise. The key findings are what will save you on the exam. A huge liver in von Gierke versus myoglobinuria, that's red urine after exercise in McArdle. Do not get these two confused. Okay, we've hit amino acids and we've hit carbs. Let's move on to fats, our long-term fuel source, and the cell's recycling center, the lysosome. I'm telling you, this is where some of the most classic, unforgettable board exam buzzwords live.
All right, first, a super quick review so the diseases make sense. Where does all this fatty acid stuff happen? It's separated. Making fats, synthesis, happens out in the cytosol, and the mnemonic is perfect. Citrate for synthesis. Breaking them down, beta-oxidation, happens inside the mitochondria. And how do you get those fats in there? The carnitine shuttle. The mnemonic here is a little dark, but man, it works. Carnitine for carnage, the breakdown of fats.
So what if that carnitine shuttle breaks?
Well, you get systemic carnitine deficiency. You can't transport long-chain fatty acids into the mitochondria to burn them. And the result is this classic triad: weakness, hypotonia, and, this is the absolute key, hypoketotic hypoglycemia. Let's break that down. Hypoglycemic is just low blood sugar. Normally, when your sugar drops, your body makes ketones from fat as a backup fuel. But here, you can't burn fat, so you get hypoketotic, meaning no ketones. You've got no sugar and no backup fuel. That's what makes this so incredibly dangerous. MCAD deficiency is similar, but it's a problem with an enzyme inside the mitochondria.
Okay, let's pivot just a little bit. What happens when the cell's recycling center, the lysosome, just stops working? Instead of breaking down and recycling old gunk, that gunk just accumulates, and that leads to what we call lysosomal storage diseases.
If you see this phrase on an exam, cherry red spot on macula, your brain needs to immediately narrow it down to two, and only two diseases: Tay-Sachs and Niemann-Pick. It's a textbook finding, caused by lipids building up in the retina.
And here's another one. A pathologist describes seeing macrophages that look like crumpled tissue paper. That is pathognomonic. It's the absolute hallmark of Gaucher disease, which happens to be the most common lysosomal storage disorder. You see that description, you pick Gaucher, and you don't think twice.
And finally, let's compare two that are so easy to mix up: Hurler and Hunter syndrome. Hurler is the more severe of the two, and the big giveaway is corneal clouding. Hunter is milder, has no corneal clouding, and it's X-linked recessive. The mnemonic here is pure gold. Ready? Hunters need good vision to aim for their target, right? So they see clearly no corneal clouding. And what do they aim for? They aim for the X, for X-linked. It's perfect. All right, deep breath. We've gone through the pathways and the pathologies. Now let's lock it all in with a couple of quick USMLE-style questions. Let's see if you can spot those buzzwords and the key features that separate these diseases.
Okay, have a look at this one. We've got that cherry red spot, so you're already thinking Tay-Sachs or Niemann-Pick. But the question stem hands you the exact clue you need to tell them apart. What is it?
The answer is B, Niemann-Pick disease. And that knockout punch was the hepatosplenomegaly. Tay-Sachs gives you the neurodegeneration and the cherry red spot, but critically, no hepatosplenomegaly. That single finding is how you nail this question every time.
All right, last one. A teenager, muscle pain, and dark red urine right after exercise. But look closely, his fasting glucose is normal. So which pathway is broken here?
And the correct answer is C, muscle glycogen phosphorylase. This is a textbook presentation of myocardial disease. The problem is locked in the muscle, which is why his liver has no problem keeping his blood glucose normal. The red urine, that's myoglobinuria from all the muscle breakdown. This is exactly how these diseases show up in clinical questions.
So, as we've seen, it's pretty incredible. A single broken enzyme can bring the body's entire complex economy to a screeching halt, affecting everything from the brain to the muscles to the liver. It really makes you appreciate how interconnected everything is. And it makes you wonder, what other complex systems in the body are resting on the delicate function of just one single critical protein?